also will discuss about the different paradigms uh, that can be used to solve problems on sequential machine. Today, we like to discuss about the parallel algorithms and parallel machines, and then we try to find out or define the different models available on parallel machines. And finally, if time permits, then we'll discuss about one example, how to solve that problem on different machines. The problem we'll be considering for our study is, for example, finding the sum of n numbers, or maybe finding the minimum or maximum of n numbers. Okay. Now, what happened? Actually, the demand of computing power is increasing day by day. You must agree on that. And the designer or architect, they try their best to improve the speed of the computers. If you observe last 30 years that they are trying their best to increase the speed of the computing power, and every 5 years what we observe, the speed of the computing speed of the machine is increased by 10 folds. But there is a limitation. Limitation is coming out because of the speed of the electronic component, and that can be used. That will be used for your component, which cannot be faster than the speed of light. So you may not be able to achieve beyond certain speed. Now, what is the alternative? Because demand will be increasing day by day. For example, initially, if you remember, that our monsoon prediction model was based on 13 parameters. Okay, and in order to obtain these 13 parameters, in order to obtain the best result using the 13 parameters, and if I have to predict something, it may need around 24 hours to solve the problem and to predict. But by that time, the monsoon cloud will be crossing the desired area. So you may not be able to predict something. Now, if I have to give you the better prediction model, then what we have to do, then we have to predict the monsoon condition based on the cloud available far away from India. Say maybe while my cloud is in Japan or near area, I must be able to tell when the cloud will reach to India. In order to do that, you need own number of parameters. By increasing one parameter, that it increases that by many fold. What we want now, that we like to increase the number of parameters for prediction, and at the same time, the speed should be, or your computing speed should be such that you must be able to predict about the monsoon rain. Okay, so this is the very difficult task. So the demand is increasing, at the same time the cost of hardware is coming down. So one solution could be, instead of using one machine, why not several machines to solve a problem? Because the cost of the machine is decreasing, at the same time demand of computing power is increasing. So what we can think that we use the several machines to solve a single problem. So what you have to do, that the problem P, if you have, and you have n machines, say problem P, and the machines, you have n machines, then you divide this problem P into n subproblems, and the each PI subproblem is attached to the machine MI. and machine Mi solves the subproblem Pi, and similarly for all I, similarly P1 solves the subproblem P1 and so on. Say let it be S1 be the solution of subproblem P1, P2, and S2 is the solution of the subproblem P2, and Sn is the solution of the subproblem Pn. Finally, these machines are used together to combine the result to find the solution of P. Okay, so that means you want to use the several machines to solve the problem simultaneously, and these each different machines, takes a subproblem and try to solve this subproblem simultaneously and then combine the result to get the final solution. And this idea is basically gives you the idea of parallel machines. Now the algorithm you design for this parallel machine is known as parallel algorithms. Okay. Now what happens is some algorithms are inherently parallel. Some sequential algorithms are inherently parallel, and in that case problem is not that difficult, and you can easily divide these problems into the subproblems, and then each person does the solution or finds the solution of the subproblems and combines the result. Say for example, if I have to do the two vector addition, say I have two vector and I want to add it. There are n machines. What I can do, this vector is divided into n equal parts, and we say it is V1 and V2. Say this addition, this two vector addition is being done by P1 processor or P1 or M1 machines, and this is done by M2 machines, and this is done by Mn machines, right? So this is inherent parallelism. So you can easily achieve our solution of these problems. But in reality, it may not be that case. So, right? You may have to. So you cannot use or may not be able to use the available sequential algorithm to solve the problem on parallel machines. Okay. So in order to do that, you may have to redesign the whole algorithm, or redesign the algorithm for your parallel machines. That is the goal of or aim of this course: how to design the parallel algorithms for different problems. According to Flynn, that whole class of machines, computer can be divided into the 4 classes. These classes are based on stream of instructions or instruction streams, and another one is the data stream. By instruction stream, we mean the set of instructions to be performed by different machines, and similarly by data stream, we mean the set of data to be used by different machines. So, Flynn's classification says the machines can be divided into 4 classes. One is known as single instruction stream, and single data stream. Next one is multiple instruction stream, and single data stream. Then you have single instruction stream, and multiple data stream. Finally, you have multiple instruction stream and multiple data stream. In short, we tell it is SISD, MISD, SIMD, and MIMD. Okay, so Flynn classifies the whole class of computation into 4 categories. One is SISD, another one is MISD, then SIMD, and finally you have MIMD. Now let us discuss about the first SISD, which is your available sequential machine basically. And here what happens that you have one control unit, you have one processor, and you have memory. So the control unit broadcasts the processor to perform a stream of instructions. The processor gets the data from the memory and performs the operation and stores the result back to the memory. This is the simple structure of SISD, and usual sequential machine works on it. Now let us discuss about MISD. Now here what happens? You have several control units, C1, C2, C3, Cn, and you have processor P1 attached to control unit 1, control unit to this, and then you have P3 and you have Pn, and you have memory. So the control unit C1 broadcasts one instruction to P1, say add, this is maybe subtract, this may be add, this may be multiply, okay, and all the processors will get the data from the same memory locations. That is all the control units broadcast or send the instruction to processors different types of operations, but the operation has to be performed on the same data. And in reality, the application of such type of model does not exist, and as a result this model dies on the spot. Now let us consider the third model, which is SIMD. Here you have one control unit and you have here processor P0, P1, P2, Pn. That control unit broadcast a single stream of instructions to all the processors. The processors takes the data either from the local memory or from the common memory based on the different models, based on the model of the machines, or it can get the data from any other processors and perform the operations. So here what happens, the data may be on different set, right? While P0 is getting the data say from the location X, P1 may be from the location Y, this may be on Z, this may be on A, and they performs the operations and send back the data into the common memory or into the local memory. So control unit broadcasts same set of instructions on different processor. The processor gets the data either from the local memory or from the common memory, or based on the network model, it is connected with the PI, another processor, gets the data from that processor, performs the operations, and sends the data into the appropriate area. So this is your SIMD model. We'll discuss SIMD later on. And then we have the multiple instruction stream and multiple data stream. Here you have basically control unit 1, control unit 2, control unit N. You have the processor P1, processor P2, processor Pn, and these processors are either connected to interconnection network or through a common memory. Then control unit 1 sends the instruction to processor P1 to perform one set of instructions, and P1 gets the data either from the local area or from the common memory or from the neighboring processors. Similarly, control 2 broadcasts another set of instructions. They need not be the same set of instructions, and P2 performs the operations taking the data from the common memory or from the neighboring or the local memory and so on. So that is the idea on MIMD. So we'll be discussing this SIMD and MIMD in detail, and most of our algorithms, or in this course we will be considering that SIMD for our study. Here you have what you have. You have one control unit, you have n processors, okay, and these processors are interconnected either through interconnection network or the processors can communicate among themselves through interconnection network, or processor wants to read the data through common memory. Okay, so you have one control unit, you have several processors. Okay, the control unit broadcasts the instructions to different processors. All the processors which are active, they take the data from the common memory, or they can get it through the data from the neighboring processor through interconnection network, performs the operations and stores the result into the desired area. Okay, the machine or model which is based on the common memory is known as shared memory, is known as shared memory model. Shared memory model, and the machines we are looking for, or that is, you have a control unit along with the end process, and this process can communicate among themselves through interconnection networks. Okay, that is interconnection based model. Interconnection based model. Now, based on the different types of interconnection model, and you get the different types of meshes, parallel meshes. Now, one could be model is which is known as P2P model. Is you have a control unit, you have PE0 and memory attached to it. You have PE1, memory is local memory, and you have PE n-1, ME n-1, and finally you have interconnection network. Okay. So this is P2P model that control unit gets send the instruction to all the processors, all the active processors gets the data either from his own local memory, or if he wants the data, it gets sends that through interconnection network, get the data of the other processors and use that for his work. There may be another model which is known as P2ME model. Here the idea is that you have control unit, and here you have PE0, PE1, PE n-1, and here you have interconnection network. Interconnection network. Here you have ME0, ME1, ME n-1. So P wants to get the data based on the instruction. It can get the data from here through interconnection network, and at the same time the P n-1 can get the data from this processor, and so this memory location and so on. So these are the three ways you can think. One is known as shared memory model, one is P2P model, another P2ME model. Now let us consider first the shared memory model for detailed discussion. Here you have n processors. N processors are numbered as P0, P1, P2, Pn-1. Control unit uses this n processors, and these processors can be made active or inactive by setting the mask. All the active processors are allowed to perform the operations, taking the data from the common memory and send the results back to the common memory. Only here, based on the different structure, we can classify the shared memory into the four groups. One is known as concurrent read, which is the weakest model. Concurrent read, concurrent write model, this is concurrent read, concurrent write model. Next one is concurrent read, exclusive write model. Next one is exclusive read, concurrent write model, and then exclusive read, exclusive write model. Now, what do you mean by concurrent read model? By concurrent read, we mean that different processors or two or more processors are allowed to read a particular memory location simultaneously. Okay, and by exclusive read, I mean that no two processors are allowed to read at a particular memory location simultaneously. Similarly, concurrent write means that two or more processors are allowed to write the data into the same memory locations. By exclusive write, we mean that no two processors are allowed to write simultaneously at a particular memory location at any instant of time. Okay. Now, in the concurrent read, concurrent write model, what happens? We are assuming that more than two processors or two or more processors are allowed to read simultaneously from the same memory locations and also allowed to write into the same memory location simultaneously at any instant of time. Now think about this concurrent read, and you observe that both in reality different processors you are allowing to write into the same memory location does not have much meaning, and it is not that easy to handle it. However, we can think about this or simulate the environment where concurrent read can be allowed. We'll discuss this part. So next model is the concurrent read and exclusive write model. That means the two or more processors are allowed to read the same memory location simultaneously. More than one processor are allowed to write on the same memory locations at any instant of time simultaneously. Now this model does not have much meaning because this is exclusive read. You are not allowing to read, which is a more simpler problem than the concurrent write. So this actually did not last for longer duration, and so we will not discuss this one. And then finally, that no two processors are allowed to read and simultaneously at the same time no two processors are allowed to write simultaneously at any instant of time. Okay, and how to handle in reality that concurrent read part? Suppose there are n processors or m processors wants to read the same memory location simultaneously. Then this can be done through broadcasting. That is, suppose P0, P1, P2, P3, P4, P5, P6, P7, simultaneously they want to read the location L. What we will do, the P0 first reads L and writes into the location say P1. Now P1 reads L, P2 reads B1 simultaneously, okay, and writes into the location simultaneously B2 and B3. Now P3 reads the data from L, P4 reads the data from B1, P5 reads from B2, and P6 reads from B3, and they can write into B4, B5, B6 and B7 and so on. So can you tell me how much time you need to broadcast or to read this N process, the location L? What is the time you need to read the content of location L by N process? Yes, the time will be ordered. First time only one processor, second time two processors will be reading the location, third time four processors, fourth time 8 processors, and so on. So basically you can find that after log n iterations, after order log n iterations, that all the processors, all the N processors will be able to read the location L. Yes. So even you do not have the opportunity to design the model of concurrency, but through broadcast we can handle the situation. Agreed? Now what about the how to handle this concurrent write part? Now there are different models exist for concurrent write. It is that one possible thing is that suppose N processor wants to write simultaneously at a particular locations. The one way could be that you put the sum of the results to be written into the location. That is, suppose P1 wants to write X1, P2 wants to write X2, and Pn wants to write Xn. One possible thing is that you take the sum of Xi and write into the location N. Okay. The another way could be that the smallest index or the index or the processor which is smallest index you allow, or randomly one of them will be allowed to write, and or you can define in any other way so that you can handle the problem of concurrent write. Now let us discuss some of the models based on the network connections, interconnection based. The first model is known as mesh connected computers. Suppose you have N processors, P0, P1, Pn minus 1. This is the N processors you have. And now these processors are arranged in the form of Q dimension. Q dimension. Say P1 to N1, 1 to N2, NQ. This is the PQ dimensions, where that N1 into N2 into NQ is your N, where N1 into N2 into NQ is your N, and P, I1, I2, IQ is the processor at the I1th location, I1th dimension, I2th dimension, and the IQth positions. Okay. Now this processor has at most 2 Q connections. That is P, I1, I2, IQ is connected with is connected with P I1, I2, Ij plus minus 1 IQ. Okay, for all j. For all j. J equals to 1 to q. So Pi1, I2, it is the index. It is the index of the processor I1, I2, IQ. It is connected with Pi1, Pi2, Pij plus minus 1 provided they exist. So in the case of two-dimensional, let us consider two-dimensional mesh-connected computer, and also we consider that it is there are 16 processors, and the processors are arranged 4 cross 4. This is the 4 cross 4 processors, and you have say P11, P12, P13, P14, P15, P21, P22, P23, P24, so these are the 16 processors. Now what we are telling, P11 is connected with P1 plus 1, plus 1 plus 1. And also this side. This connection is bidirectional, that's why it is taking plus minus sign. Okay. So this is the today mesh connected computers. Now here you observe the processors what we are putting, they are Pij form. But in reality, processors are numbered 0, 1, 2 up to n minus 1. So there is a need of introducing some indexing scheme so that Pi can be mapped onto Pjk. Okay, so there are several schemes exist for this type of indexing. One is known as row measure indexing scheme. Say Pi is connected to Pjk. Pi is connected. Pi is the processor with index I, and Pjk is the processor in the jth row at column and kth column. Kth column. Now, indexing scheme is, since it is a row measure indexing scheme, that number should be like that: P0, P1, P2, P3, P4, P5, P6, P7, P8, P9, P10, P11, P12, P13, P14, and P15. Right? So we have to find out the relationship between, say, P32 should point to P9, or P9 should occupy the position or the processor at the third row and the second column. So what is the relationship between I, J and K? I is equals to is it okay? That is, when j is equals to 1, k is equals to 1, then it becomes 0, I is equals to 0. Then when j is equals to 1, k equals to 2, k equals it is 1, and when j equals to 2, k equals to 1, that is 4, and so on. So this is the relationship between I and j and k. Similarly, we can have the numbering scheme as a column measure indexing scheme. There is another indexing scheme we can define, which is known as snake-like row measure indexing scheme. In the snake-like row measure indexing scheme, the scheme looks like this. Okay, that is in the form of snake or rope. And in that case, what should be the relationship between Pi and Pjk? Relationship between Pi and Pjk. Now you observe that when the row number is odd, it is as earlier as, that is Pi is equals to I is equals to j minus 1 n plus k minus 1 if j is odd. Agreed? Now if j is even, then what? Is it, can I write j minus 1 into n plus n minus k? Let us see. When 2, 1, that is 4 plus, yes, 4 minus 1 is 3, 4 plus 3 is 7, and then when it is 2, 4, then this becomes 0 and this is 4, yes. When j is even, then it is j minus 1 n plus n minus k. So this is snake-like row measure indexing scheme, and similarly you can define snake-like column measure indexing scheme, where this will look like this. This is known as shuffled row measure indexing scheme. Suppose the processor Pi occupies the Pjk positions in the row measure indexing scheme. Suppose processor Pi occupies in the location Pjk, that means that is the jth row and the kth column of the row measure indexing scheme. And the binary representation of I is B1, B2, B3, BQ. Then shuffled of I is defined by B1, BQ by 2 plus 1, B2, BQ by 2 plus 2, BQ by 2. Okay? Then what we will do, that if it is I dash, then Pi dash occupies the location of Pjk in the shuffle row measuring scheme. Okay? The idea is, suppose Pi occupies Pjk, that means jth row and kth column of the two-dimensional array under the row measure indexing scheme, and I, if I convert, is in the binary representation of it is B1, B2, B3, BQ by Q. Then we define the shuffle of I as B1, BQ by 2 plus 1, B2, BQ by 2 plus 2, and BQ by 2. Then this is I dash, so Pi dash will be occupying the position of jth row and the kth column. Row measure indexing scheme: P0, P1, P2, P3, P4, P5, P6, P7, P8, P9, P10, P11, now that let's consider I 0, 0, 0, 0, and this is your I. What is your I dash? I dash is same thing, 0, 0, 0, 0. You have 0, 0, 0, 1. And this will come here, so it will give you 0, 0, 0, 1. Then you have 0, 0, 1, 0. This will be 0, 1, 0, 0. Then you have 0, 0, 1, 1. This will be 0, 1, 0, 1. The next one is you have 0, 1, 0, 0. This will be 0, 0, 1, 0. You have 0, 1, 0, 1, which is 0, 0, 1, 1. Then you have 0, 1, 1, 0. So it is 0, 1, 1, 0. You have 0, 1, 1, 1. Still it is 0, 1, 1, 1. Then you have 1, 0, 0, and this is 1, 0, 0. Then you have 1, 0, 0, 1. So it is 1, 0, 0, 1. Then you have 1, 0, 1, 0. This will becomes 1, 1, 0, 0. This is 1, 0, 1, 1. So it becomes 1, 1, 0, 1. Then you have 1, 1, 0, 0. This becomes 1, 0, 1, 0. Then you have 1, 0, 1, 0, 1. It is 1, 0, 1, 1. Then you have 1, 1, 1, 0. So this is 1, 1, 1, 0. And you have all ones, which is all ones. Okay. So in that case, the shuffle row measure indexing scheme becomes is P0, P1, then this is 2, 2 is mapped to 4, so this becomes 4, this becomes 5, this becomes 2, this becomes 3, this becomes 6, this becomes 7, this becomes 8, this becomes 9, this is 10, this is 11, 12, 13, 14, 15. So basically you can think about this way. So in generalized form, so you can define, suppose you have this side 16 processor, this side another 16, this side 16, so it is 32 cross 32, and here this 16 processor you can define like this, you can define like this, and so on. Okay, so here this is P0, P1, and here P15. Here you will have P16, P17, and here 31. and so on. You observe that for the 2D mesh connected computers, you have at most 4 connections. Now, in the boundary, since you may have 2 or 3 connections, and for example, you have P0, P1, P2, P3, P4, P5, P6, P7, P8, P9, 10, 11, 12, 13, 14, 15, so P9 you observe there exist 4 connections, but in the case of P0 you will have the 2 connections, while P8 is having 3 connections and so on. Now there is another model which is known as wraparound mesh connected computers, and here it means that P0 is connected with P12 or P13 is connected with P1 and so on. Similarly is the case with this. That means every processor will have 4 connections. Will have the 4 connections. So iliac port or iliac machines are of this type. And this model, even though it looks a little complex, but it has the homogeneity. So it is easy to understand or implement the algorithms on this model. You remember here for Q dimension mesh connect computer you need the 2 Q connections. Now the next model is known as perfect shuffle computers. Let us assume there are n processors P1, P2, P3, Pn-1. These are the n processors, and let us assume the binary representation of I. So for simplicity, let us assume that n is equals to 2 to the power q, right? If n equals to 2 to the power q, can you tell me what should be the number of bits? Yes, there will be q bits, and let us assume that iq minus 1, iq minus 2, this is I0. Okay, the binary representation of I can be expressed in the form of iq minus 1, iq minus 2, and I0. Then the Pi is connected with 3 processors provided they exist Pj, K, and Pl, where J is obtained by the operation known as exchange. So exchange of I is nothing but iq minus 1, iq minus 2, I1, I0's complement. Okay? The exchange of I, J is nothing but the exchange of I, where exchange of I is defined by iq minus 1, iq minus 2, I1, I0. Now K is known as shuffle of I, which is defined as I0, iq minus 1, iq minus 2, I1. And L is unshuffle of I, which is defined as iq minus 2, IQ minus 1, I0, IQ minus 1. Okay, so basically every processor is connected with at most 3 processors. You remember in the case of two-dimensional mesh, every processor is connected with at most 4 processors. Here, that means you need the less number of processors, less number of connections between for any processors. Okay. Now, in order to illustrate or this example, illustrate it, let us consider n equals to 8. N equals to 8, and let us see how it looks like. So you have P0, say processor index 0, 1, 2, 3, 4, 5, 6, 7. This is the 8 processor we have taken. Then you have to obtain J, which is exchange operation, exchange of I. You have K, which is nothing but shuffle of I. And you have L, which is unshuffle of I. Okay, so exchange of I is 1. This is nothing but 000. This is nothing but 001. This is 010, 011, 100, 101, 110, and all ones. So exchange is nothing but this is 0, this is 3, this is 2, this is 5, this is 4, this is 7, and this is 6. Shuffle of I, this is 0, this is 4, this is 1, this is 5, this is 2, this is 6, this is 3, this is 7. Unshuffle, this is 0, this is 2, this is 4, this is 6, this is 1, this is 3, this is 5, this is 7. So I is connected with exchange, shuffle and unshuffle. Now if I have to draw it, then let us draw it P0, P1, P2, P3, P4, P5, P6, P7. Now P0 is connected with P1 and P0. P1 is connected with P0 and P4. P4 and P2. P2 is connected with P3, P1 and P4. P3 is connected with P2, P5 and P6. P4 is connected with P5, P2, P1. P5 is connected with P4, P6, P6 and P3. P6 is connected with P7, P3 and P5. P7 is connected with P6, P7 and 7. So this is the structure of perfect shuffle computers. Now here you observe that one thing I want to tell you, that perfect shuffle computers, not only it has the less number of connections, it is based on the two important properties. One property is that if D is available, data D is available in Pi, and after Q shuffles, when n is equal to 2 to the power Q, when n is equal to 2 to the power Q, after Q shuffles, n is the number of processors. If after Q shuffles, the data will come back to its original positions. So property 1 is that if there are 2 to the power Q processor and Q processor, then after Q shuffles, the data of each processor would come back to its original positions. This is because this is a Q bits shuffled Q times, so it goes back to original one. The second property is that suppose data X is in Pi and Y is in Pj. Data X is in Pi and data Y is in Pj, and the binary representation of I and binary representation of J, they differ only in n minus kth bit or q minus kth bit, right? The binary representation of I and binary representation of J, they differ only in the q minus kth bit. Then after k shuffles, the data will come back to the adjacent locations, because that, say you have I q minus 1, I q minus 2, and here you get x, not x, say I, and then here you have I0, and this is same, here it is I's complement, and here I0. After the shuffle, this will come here and this will come here. So they will be adjacent location. They will be in adjacent location. Okay. So this perfect shuffle computers, most of the algorithms on perfect shuffle computers are dependent on these two properties. One property is that if that data X is in Pi and Y is in Pj, and the binary representation of I and binary representation of J differs on n minus k only in one bit, q minus kth bit. Then after k shuffles, the data will come back to the adjacent location. And another one is that if you have 2 to the power k of q process, then after q shuffles or q unshuffles, data will come back to the original positions. Okay. Now, in the next class, what we like to consider the model, we like to consider, first one is that butterfly model, second one is hypercube, and third one is on cube connected cycle, and the next one is the tree model, and then one-dimensional pyramid and two-dimensional pyramid model. So the models yet to be considered are models of SIMD machines. We have already covered base connected perfect shuffle computers. We will be doing the butterfly, hypercube, and then cube connected cycle, tree, linear array, one-dimensional, pyramid model, and then you have two-dimensional pyramid models. So these are the models, well-known models, which we like to consider. We have already discussed about the mesh connected and perfect shuffle, and these models we will be discussing tomorrow. Thank you.